Hi, my name is Alex, and I'm here again, this time to talk about the TensorFlow eager execution runtime. This is a very broad topic, and there are lots and lots of things we could cover, so I'm going to lightly graze many different parts of our code base. I'll give you a lot of function names and file names and things like that that you can use to familiarize yourself with something. But if you're in the room right now, by all means ask questions. There's some buffer time at the end to account for variability here, and I think the more we can maximize shared understanding of this stuff, the better. So the way I thought about we could go about this is to do a very deep dive on what actually happens in TensorFlow, starting from TF2, when you type a very simple line of code, in this case a tf.nn.relu of some Python numbers. And I think if you were to start doing this, probably the first thing you'd do is grab the TensorFlow codebase to find where would we define relu. And if you do that, you'll find that we have some definitions of relu in Keras, but you won't find a single definition of relu itself in core TensorFlow. And that might be a little surprising at first. It might put a damper on this whole let's find out what actually happens when you run relu business. But the way relu comes from is because it's an op that we've implemented in C++, and we didn't need to put a complicated Python API around it. We can just generate the Python code to call relu. So the way it's actually defined, it's defined using the same mechanism we use to register all the ops in TensorFlow. So for every core operation in TensorFlow that's visible to the runtime, we have a registration that looks like this. Register op, it takes a name, and you say how many inputs, how many outputs, what attributes it has. If you want to know more about attributes, what things are allowed in there, they are how we can make our ops polymorphic and have the same operation have different types of outputs or different numbers of outputs and things like that. There's a lot of documentation about this on tensorflow.org if you search for how to define a new op. And another interesting thing in there is that we also register a shape inference function. Relu, thankfully, is one of the simplest ops we have. It just has one input, one output. They have the same shape. So we can use a pre-built shape inference function that just says the shape does not change. Other ops will have vastly more complicated shape inference functions. And the nice thing is that we can run these functions offline while we're building graphs without actually having the values of any tensors and still be able to prove things about the shapes of intermediate tensors and outputs of your computation. This is maybe the best tool we have for catching bugs now. So if you want to look at the shape inference code, that's where you'd hook into. Now that we have that registration, we run some complicated code that generates Python code to actually call relu. And if you look in Basel gen files, you'll find a file named gen.nnops.py, and this file has the actual def relu that we call. And as you can see, it's not pretty, and there's a lot of stuff going in there. The first line deals with dispatching, so that we can define relu not just for normal tensors, but also optionally for sparse tensors and reged tensors and other composite types. The second line has tf export, and what this does is define the TensorFlow public API. Every symbol that you get when you're using TensorFlow by tf dot something is defined somewhere from a tf export decorator like this one. There will be a future video on how exactly this works and why we do things this way instead of relying on Python's normal namespacing mechanism, but you can probably guess that it's because TensorFlow is very complicated. But essentially you'll see this. And this generated code for relu, it has a bunch of cases in it. There are roughly 4. You have an eager fast path, an eager slow path, you have a graph mode path, and kind of a side hook for the symbolic execution. But here, let's focus on the eager paths. And the first thing that we're actually doing here is we're checking to see if we're in eager mode or not. And to do that, we look at this context thing. This context thing is part of the core of the TensorFlow v2 runtime. It's the moral equivalent to the session, but it's longer lived in the session and represents more things. So what is it? From Python, the context is this class that's defined in a file called context.py, and it's a collection of a lot of things that your Python program needs to be aware to connect to the TensorFlow runtime. It stores things like, am I in eager mode or in graph mode? Or if someone used a with tf.device decorator, what device am I supposed to be executing code in? And it stores things like, what's your name scope, and many other things. And all of this information that the context stores in general, the things that can change during the execution of a program, they're all stored in thread local stacks. Usually stacks, because we have these nested things like with TF the device, with TF the device, with TF the device, so you'd like to be able to pop the stack to go back to where you were. And thread local, because it's very important to us that the TensorFlow runtime itself be thread agnostic, so that if you write two threads and one is doing a reinforcement learning learner and the other is doing an agent that's talking to some game, when the agent wants to use its GPU, it shouldn't necessarily make the learner use the GPU and vice versa. Providing some kinds of isolation between the threads is what we felt like was the right way, so that at least each single thread can feel like it's its own like single-threaded Python program. We use this a lot in distribution strategies, like mirrored strategy uses a lot of threads under the hood, so it's really important that things are thread safe. In the Python context, essentially, it mostly is a wrapper around a C++ context that's available through the TensorFlow C API. And this is the core thing. And it has a bunch more methods than just these. Like it can do a lot more things than just list and devices. One thing I'd like to call out is that right now, there are some things that are done in Python, like storing whether you're in eager mode or in graph mode, and some things that are done in C++. And it's not the set of things that are done in Python and set of things that are done in C++ are likely to change. I think as TensorFlow evolves, more and more things should migrate from the Python context to the C++ context, which will make things more language agnostic, but also faster. And if everything in the context was in C++, then all the generated Python code could have just been C++ code, and would be able to get out of the overhead of executing Python much sooner and remove, performance problems in our APIs. So once you know that you're in eager mode, we try to do this fastpath execute. In this, the fastpath is some complicated C code that mostly does the same things that the fallback case is trying to do. So I don't think it's necessarily worth reading that. I would rather look at the simpler code in the fallback path. And it's here. So this is where we actually implement the relu function. And what are the interesting things here? First, we have this function called args to matching eager. And what it does is it takes a bunch of tensors, a bunch of things that can be tensors, converts them all to tensors of the same d-type. In the case of relu, there's only one, but in the case of any other ops like add or matmul, they take multiple inputs, some of which might be tensors, others might be NumPy arrays, or Python lists, or variables, or other objects that you can convert to a tensor, but they are not necessarily tensors. And this is the thing that's responsible for canonicalizing everything. Then, once we have, but here you might want to stop me a little and ask, what is a tensor at the level of the TensorFlow runtime? And the eager tensor class is a thing that's half implemented in Python and half implemented in the Python C API, but it's a relatively thin wrapper around this thing that we call tensor handle that you can see in our TensorFlow C API. And this tensor handle, it represents a potentially yet to be computed tensor, which is going to live on some device. And we know what device it's going to live on because we know what device we executed the operation that generates the tensor on. And there are roughly three things you can do to a tensor handle, really. You can ask about its shape and d-type and stuff. That's one. You can give it to execute. That's another one. And you can copy it to a device. Also, I guess there are four things. And the fourth thing is you can ask, hey, what is its value? And when you want to force the evaluation of its value, the TensorFlow runtime might have to pause until it can, give you the result. It might need to copy that tensor for some remote device and do all sorts of other things. But once you're done, you get a TF underscore tensor, which is essentially just a pointer to some data. But every other operation that is not looking at the value of the tensor is something that the runtime is free to delay, reorder, as long as it respects the intended semantics of your program. And this is very important because when you're working with things like GPUs and TPUs, you'd like to be able to dispatch operations to run in the hardware as quickly as you can in a way that's asynchronous. If the Python thread can race ahead of the GPU as it's executing operations, we can fully utilize the GPU hardware and get the maximum performance. And even with the eager runtime, we can do this if the GPU kernels are sufficiently heavy. There are a few cases in which we need to copy tensors, even if they're local on the CPU. And some of those cases are going away. Like currently, we copy string tensors every time you try to look at their values, because TensorFlow's internal string representation is a complicated C++ class, and we'd like to have an ABI stable C type. we're actually changing our internal string representation. There's an RFC you can look about it that will make the internal and external representations both be an API stable C type. But internally, what is a tensor handle? And this is in fact very, very similar to the first implementation of tensor handle. Now it's like hundreds of lines of code spread across many files. But all that you really need in a tensor handle is to know what device it's in and what data you have. And the data can either be a concrete tensor, a value that has already been computed, or a future that might be computed later because it's remote or asynchronous or on some other device. But the core of it is this. This is the future that we handle around in the representation. The current code is much more complicated, and you might want to look at it to see why it's complicated, but the core idea is there. So, pop in the stack. You now know what a tensor is, and you've probably figured out that converting that list of Python integers to a tensor is not terribly hard. There's C code that does that. And now it's time for us to execute relu. Great. Here's one thing to note about how the TensorFlow eager runtime works, which is that this line that is selected there is not a non-controversial choice. Overall, there are two ways we could have gone about this. We could have had a closed domain API in which TensorFlow would export a symbol called relu, another called matmul, another called conv, etc. Or we could have this open domain API that we have here, where we have a symbol called execute that takes the name of an operation, relu, and a bunch of metadata about it. There are advantages and disadvantages to both cases. In general, the closed domain case, where you just have a single endpoint in your API for every operation you want to run, that is easier to make fast. However, it's a little tricky in TensorFlow because the pre-existing graph runtime has a few layers of interaction between a node in the graph and the actual kernel that it executes. And indeed, between TensorFlow versions, we can, without breaking graph-depth compatibility, replace some kernels. Some things that were handled by a single kernel now have to be handled by like many multiple kernels. So to preserve this layer of interaction, we felt like it was more natural to have this API that is an open domain API. However, as you can see, just by the fact that there's a string in there, executing this can only be so fast, because we need to somehow take this string and these attributes and some properties about these inputs and turn that into a kernel. And that means that we can definitely not execute kernels any faster than it takes to at least hash that string. So, there are trade-offs here, but we felt that preserving the flexibility that you have in graph mode was the most important thing here. So, how do you actually use execute? When you call this line in Python, what actually happens? And execute is something that is defined in the TensorFlow C API. And to use it, you do something like this. You first create a status so that you can find out if things failed. And then you make a new op, you add inputs, you set attributes, you allocate some memory to put pointers to the return values, and then you call execute, and finally you delete that op. And so this is fairly straightforward, and if you're familiar with the TensorFlow C API for building graphs, you'll see that this is very similar to that C API. This is about as good as you could possibly get for Python code in an open domain setup, but it's a little sad here that when you build a TFE op, you need to add the inputs to that op. This means that if you're executing an op in a tight loop, you have to have the same inputs on every iteration of the loop, or you have to allocate a whole other TFE op. For Python, we really don't have a way of making this better, but for other languages like Swift, or languages that have access to a compiler, we should be able to cache the dynamic bits that involve making a TFE op and separate them cache the static bits that don't really change, like all your matmuls are the same, and separate that from the dynamic bits, which are the inputs that should actually change. And if you do this, we could make, in principle, this open domain approach as fast as a closed domain approach. And this is maybe a minor refactoring that we should do at some point. So what does execute do? If you go for a few layers of APIs, you end up on this function called eager execute, and it has a lot of things here. The first interesting one is this maybe update op device, which is, you might call it the placer, where we get to decide where we're going to execute each operation. TensorFlow has some complicated heuristics. In general, you can think of it as, If you're operating on a resource tensor, we'll run your operation on the device that has that resource, because any other thing will fail. Otherwise, if you have a tf.device annotation somewhere, we'll run it there. Otherwise, if you don't have any of those things, we'll see what devices are available to execute this operation and run on whatever device you think is going to be the fastest, which is how TensorFlow gets away with using a GPU for you, even if you don't specify with tf.device GPU in there. And then you have like some forks in there about are we local, are we remote? And once you do know that you're in the local case, what we want to do is very quickly do that string processing that we needed to do to find what kernel we should be executing. And there's a fast code that takes the attributes and the name of an op and gives you a cache key that is looked entirely in the context and where we store the kernel. And here you might think something's a little funny because, you know, usually you think of operations as functions, not as classes, but clearly there's like a kernel and device class in there. So we probably have an object. And the reason is that for many types of kernels that we want to execute, especially things involving GPUs, but also some stateful kernels, you want to keep some state in that object. Ideally, that state will be managed by the runtime via the resource managers, but that doesn't always happen now. And once you have a kernel, the kernel tells us on what devices it wants its inputs on. You would think that the kernel would want its inputs all on the device that it's executing, but that turns out to be too narrow of you. For some kernels, especially GPU kernels, you might want some inputs on the host CPU that's attached to the GPU. And the reason is that imagine you're a GPU kernel for generating a big matrix of random numbers. You'd like to know how many numbers you're going to generate so that you can run the memory allocation before you enqueue your CUDA kernel. So if you were to do that, if the shape of the random number vector you're going to generate, if that's in the GPU, you'd need to fetch it back to the CPU to do that allocation. That would be terribly slow. So instead, TensorFlow says, I expect that input to be on the local CPU. And this is the function that validates this. But in this case, if you're also trying to run a large convolution and one of the inputs is on the CPU, this maybe copy will move that input to the GPU for you, which is faster than just running your convolution on the CPU. And then finally, we get to decide whether we're in sync or async mode, where we first create this node that represents all the computation that has to happen to execute this kernel. If we're async mode, we throw this in a queue and return control immediately. If we're in sync mode, we run it now. This async sync here is complicated because there's another layer of asynchrony that's separate from the fact that our GPU runtime is itself asynchronous. This is kind of a patch to make the TensorFlow CPU runtime, which is currently synchronous, act asynchronously to try to get a little more performance in the eager mode. It's a little sad because you lose your error messages once you get very asynchronous there, and you currently do not run shape inference in this asynchronous mode. I think as we rework the TensorFlow runtime, which the team has a large effort to do now, we have a chance to fix this and have a single code path for synchronous and asynchronous. But for now, we have this patch. And then finally, now we have the kernel, we got to call it. That's easy, right? So to call a kernel, you have to make an op kernel context. And to do that, you need to fill this param struct, which I put here, which you can clearly read in the slides because it could definitely fit with a very large and readable font. So we don't do that. This is sadly something that the original TensorFlow API for kernels had only one caller, which was the TensorFlow Executor. So it was very easy to just add parameters and make the calling convention harder and harder because there was only one place to fix. We're now trying to trim this back and simplify it, so it will likely get better. But for the eager runtime, we have this class kernel and device that knows how to call a kernel, requiring a lot fewer things about it. Mostly all it needs is the inputs, a place for you to populate with outputs, and some information in case you want to profile. Things about how long it takes to execute each node or do a step or what graphs you're using if you're executing functions and things like that. So now that we have this, we can run the kernel. So what do kernels look like? ReLU happens to have one of the simpler kernels we have in TensorFlow. it's a unary element wise off. We have a base class for this that handles a lot of the logic around memory allocation, buffer reuse, so that tf.relu by default will reuse its input buffer if the TensorFlow runtime knows that no other op yet to be executed is going to need this. But once all the boilerplate is dealt with, all that this kernel has to do is execute the functor. And this is another place where you'd be surprised that we use an object where you think we should use a function, because in principle, relu is just a function. It doesn't keep any state. There should be no reason for us to make an object for it, except C++ does not let you define a templated function, declare a templated function in a header file, but define it in a C++ file. And this is something very useful for us because, as you can see, device is a parameter in there. And one of those devices is GPU devices. And for GPU devices, we'd like to put the function in a file that we're going to compile with a CUDA compiler. And we would like to not compile our entire code base with a CUDA compiler. So being able to define this functor in a single place where we can generate a whole specialization of this class without having access to a CUDA compiler, but have a file on the side that's just going to fill in this implementation after running the CUDA compiler is very useful. And as you can also see here, TensorFlow kernels, they tend to be highly templated. Most are templated like this one, based on the device that it's going to execute on, and on the D types, so that we generate fast, specialized code for every core numerical type supported by TensorFlow, which is an incentive to keeping the set of core numerical types supported by TensorFlow relatively small, as otherwise our binary size would grow. But this has the nice side effect that the code generated is very fast. And one of the things that makes us generate very fast code for this, which you will see if you look into the implementation of the functors, is that we can use eigen to generate this code for us. So the relu functor in particular is very easy to write because it's just a component-wise max between the tensor you have in your input and 0. And eigen turns out to be a very useful tool to write this. It lets us write this code once. It will generate specializations for every D type we are interested in, and also for CPUs and GPUs. For this particular operation, you could probably write it in fast assembly language yourself, or SSE intrinsics or something like that. But for more complicated operations like softmax and others that might have interesting intermediate values that need computing, being able to just have this code be generated for you instead of requiring that you write all the device-specific and type-specific things can save a lot of time. Also, eigen in its core has very, very fast gem, which is the core like basic matmul that is inside most of our very expensive kernels. It ends up being a very large asset in making TensorFlow go fast. So that was it, really. It only took us, what, 20 minutes to get through executing relu. I think TensorFlow can do it a little bit faster than that. But in general, this is kind of like what the stack of things looks like as you're executing operations eagerly. Of course, if you've been following this for a little bit, you should know that we can do better than executing operations eagerly. In TensorFlow, we have tf.function, and we have graphs and other things that can get you a lot more performance by, instead of going down and up that stack for every single operation, going down once and executing a lot of operations. Also, this lets us do optimizations and stuff. So how do we run functions?
Yes, before you proceed, so you mentioned briefly about the async mode. So is that something that is user configurable because there's like context async flag?
I don't remember right now if there's a public API to make it user configurable or not, but there's an internal API to make it user configurable.
I believe there was in enable eager execution, you could set it. So I think you could set it in V1, but it might not be exposed directly in V2.
Yes, Taylor is correct. I think I know how to expose it in V1 and do not know how to expose it in V2, but there's probably a way. Or maybe there's not a way yet because we're still treating it as experimental. I'm not sure. Regardless, the way it is now, I don't think it's something we should rely on in the long run. So I'd rather be able to iterate on it a little longer until we start recommending it as the way for people to get performance. So,
what is the difference between eager flow, slow and fast path?
It's mostly that the fast path has special case some types of tensor conversion into fast C code. So if you pass a list of Python floating point numbers, we can convert that to an eager tensor without hitting any Python code. And that will save you quite some time. Okay, so most of what we saw right now for the case of executing a single op, also applies to executing a function. So a function itself is an op named partition call, and you will execute that op, like the tf.function internals will execute that op, just like how we just saw how to execute relu. And so the first half, until you get to the kernel and device run bit, is all the same. It's just that that kernel implementation is particularly interesting. And function calls in TensorFlow, they look relatively simple. We have inputs, we have outputs. We have attributes that tell TensorFlow what types of inputs we have, what types of outputs we have, and we have a function. There are some things in there that seem a little tricky, like there's all sorts of configuration we can pass. I actually forgot what's the difference between config and config proto in there. But essentially, this is the big entry point to executing functions in TensorFlow. But what this, if you go look at the kernel of this op, what you'll find is that it mostly just forwards things to the function library runtime. And the function library runtime is this core bit of TensorFlow that knows about functions. It can do things like instantiate and run, pretty much. And also create kernel, which you usually do between instantiate and run, since that will let you, for the function library runtime also knows how to execute operations that are not functions. So what does instantiate mean? And instantiate mostly runs all the graph optimizations that we might want to run on that function to take code that you enjoyed writing and turn it into code that the executor will execute very quickly. Most of this processing happens in this process function library runtime instantiate multi-device call, where we run all sorts of graph transformations. This is, if you have a TF-XLA bridge happening, it will run the transformations related to TF-XLA bridge. It will run the TensorFlow placer. What a TensorFlow placer does is it takes a graph, in this case a function graph, that has devices assigned to some of the nodes, and it spits out another graph that has devices assigned to all of the nodes. It does this by following a very similar algorithm to the one that I described earlier for individual ops. So if you have a resource, we'll place that op next to the resource. Otherwise, if you have specified a device, we'll respect that device. Even if you partially specify the device, we'll respect the partial device specification. And finally, we'll we'll group things by collocation group. The TensorFlow graph language allows you to specify collocations, even though these have very non-intuitive consequences. Because by collocating a node A with a node B, you can actually move where node B is placed. Because the placer is not aware of the direction of the collocation arrows. It just groups all the collocated nodes into a bag and finds a device that can execute all ops in there. So this can have very fun consequences, like a bug I helped fix a while back, where if you try to speed your distributed system by always collocating the variable initialization code with the remote device on which the variable is in, and you can accidentally say, please always collocate the initializer for my GPU variables on the GPU, which can be trouble if you some of your initializers have operations that cannot run on the GPU. You now have silently moved your variables to the CPU, which probably is quite a performance degradation. So it's very subtle, and in TF2, we're trying to move away from using collocation constraints inside TensorFlow, and we're definitely moving away from encouraging people to use collocation constraints outside TensorFlow. I'd rather you be more specific about what devices you're using, or even better, use something like a distribution strategy that is aware of all these bugs and collocations and can work around them for you, instead of trying to replicate this functionality yourself. And once you have placed the graph, we can run the partitioner that takes a graph that has nodes for many devices and returns many graphs, all of which have nodes on a single device only. And to do that, if there was any edge that went from one device to another device, that gets replaced with a pair of sends and receives. This is also where we run Grappler and all the function inlining and optimization passes that the last training section with Eugene was covering. But yeah, so this does a lot of heavy lifting, and indeed, the partition call op puts a cache in front of instantiate to make sure that we don't call it twice for the single function, because otherwise it would be very slow. And once we've instantiated the function, we can go to the other main method in the function library runtime and run it. So In general, as you can tell by the name partition call for the op, our functions can be on multiple devices. And at this point, at least, the code has simplified enough, and this is actually snippeted from the core runtime, even though the core runtime has a lot more error handling going on, that all we have to do to run a function on multiple devices is to just run a function on a single device, run n functions each on a single device, and trust that they all know how to talk to each other to make the sends and receives happen. So there's some thing called a rendezvous, and if you read the TensorFlow code base, you'll see lots of references to it that's responsible for making the sends and receives all aware of each other. We have rendezvous that know how to deal with single host and with multi-host, and there are lots of tricky and interesting bits into how they relate with what is the correct lifetime of a rendezvous, how do you shut down a rendezvous once you want to shut down TensorFlow computation because maybe some kernels failed. And if some kernels failed and something is blocking on receiving a tensor, they're never going to get that tensor. So we probably need to shut that operation down gracefully. And there's a lot of cancellation related logic in there. But it mostly, at the level of the function library runtime, you can just run your n functions one per device and forget about it. And running a function on a single device mostly consists of bringing up this TensorFlow Executor and calling run in it. And you'll see that you have things named run async and done callbacks. In general, we treat all of these things as asynchronous so that we can release the calling thread as quickly as we can so that you can keep on running more computation on it. Especially if you have nested function calls, treating these things asynchronously is quite the performance improvement. And here, I could dig into the TensorFlow Executor, but that code is fairly complex, and you have a simple core algorithm, but it's really hard to pull it out of there. And I think the main reason why it's hard to pull it out of there is that the executor grew together with the implementation of control flow in TensorFlow, and specifically, the details that we had to do to implement while loop kind of obscured a lot of the core functionality of the executor. It now is aware of frames and a lot of other complicated things, and you have multi-dimensional pending counts. So I'm not going to snippet that code, but I'll say that if you want to read it, go for it. It's very interesting, highly asynchronous, highly parallel interpreter. But I'll just give you some of the highlights of what's happening in there. And its input is a large bag of nodes, and there's no output. Anything that you want to get out of it, you get out of it through a send or a receive. I mean, technically there are outputs, but by far most outputs in the common case of TensorFlow are handled through sends and receives. And the end state for the executor is that all nodes must execute it, or an error has happened. And inside TensorFlow, the core runtime, we have no error recovery. So any error will shut everything down. This is sometimes unfortunate because some parts of the TensorFlow's higher level APIs rely on errors for the common path. For example, tf.data raises an error once it reaches the end of a stream, which means that you can't really easily have a single graph that exhausts a single iterator, does some things, and then runs another iterator. Because by the time you've exhausted the first iterator, an error is raised, and TensorFlow will shut everything down. There are ways of interacting with tf.data that do not involve using the iterator get next stop, which can fail. And we use those inside autograph to make it easier for you to write code that can recover from these failures and, well, not recover from these failures. It will see no failures when iterating over multiple iterators. It's quite nice. TF-data has all these cool little combinators like take while and reduce, and you can thread together 3 of those to simulate a while loop with breaks. But anyway, popping the stack here, the core algorithm of the executor is while there are some nodes that haven't been executed and no errors have happened, execute a viable node, and once that node finishes executing, you mark all of its output tensors as ready, and there's some bookkeeping in there that once you mark a tensor as ready, you look at what ops are going to be made executable by marking the tensor as ready, which marks other nodes as viable, and this just recursively applies. In the executor itself, it's not a single thing. It runs on every thread that is executing an op as soon as that op finishes executing, and it dispatches all the execution to another thread pool. It's kind of surprising that this is happening because this means that TensorFlow cannot really be run on a single thread. But some interesting noteworthy things about the executor that you might have guessed from my comments so far, but require some thinking, I think. One is that the executor is greedy, not lazy. And if you're familiar with TensorFlow, it looks very lazy, but it mostly looks lazy because we do very aggressive graph pruning. And once you start putting control flow and function execution and a few other things in the executor, it actually pays off to have a mental model that says that first pruning happens and then greedy execution happens. Otherwise, you can trick yourself into thinking that some things are not going to be executed when they are in fact going to be executed. Like my favorites, if you have a conditional, and one of the branches of the conditional depends on a value that is not in the conditional, that value is unconditionally executed, even if that branch is never executed. Which, if the executor were lazy, that would not be the case. But the executor being greedy also makes it easier for you to be able to reason about stateful operations, which is very nice, given that those exist. Another thing is that this executor, it only looks at very local information. Like the only bit it has for each node is whether it's ready or not. So often, there's nothing preventing it from choosing very suboptimal orderings of things to do. Like if you need to fetch a lot of tensors from a parameter server, the executor is just as likely to fetch the first layer's tensor as it is likely to fetch the last layer's tensor, because none of these things have any dependencies on them. And it can be quite tricky to teach TensorFlow to actually choose the optimal orderings of things to execute. And as I was saying earlier, this executor is this thing that there's no single executor thread. It just runs on every thread as soon as it finishes executing an op. So it's kind of this highly parallel little monster. So this is it for most of the core TF runtime. I just had a few topics that I couldn't really fit very well that I wanted to cover in this presentation just to generate some documentation. One is host versus device memory. As I hinted at earlier, when you partition TensorFlow, it takes a graph and it spits out n graphs, one graph per device. Each graph per device gets its own executor. But how do you deal with the fact that some GPU ops take CPU tensors? So we make a distinction between when you specify an input to a kernel, you can say that that kernel expects that input to be in host memory or expects that input to be in device memory. And so in fact, the executors for the GPU device can be, and most of the time are, running a lot of CPU operations on CPU tensors, only they call those tensors GPU tensors in host memory. And so if you look at the TensorFlow code, you might sometimes see things like a distinction between the device a tensor is in, and a device its memory is in, and a device its operation is in. And this bookkeeping is necessary to avoid mixing these things up. And incidentally, all resource handles are in host memory. But this has a very sad, unintuitive consequence that we need to fix, which I call, and I think other people call it, just like TF in 32 problem, which is that most of the things that GPU ops take as host memories are shape related. Things like fill and zeros and random, normal, they all take a shape and they fill that shape with whatever values you want. But the shapes are not static. They're often computed based on other shapes. The simplest case is when you just use zeros like or something like that, where you take a tensor, take its shape, and use that shape to fill in another tensor. But sometimes you're going to reduce some dimensions on the shape, broadcast, do some other things. And TF has this rule where by default, it will place every GPU-capable op on a GPU device. And if you want finer-grained control, you just take a large block of code in TF and you wrap it with a tf.device, which also means that every op that happens inside a block of code gets placed on that device. So if you allowed TensorFlow to have GPU kernels for int32 tensors, we would keep bouncing these int32 these shapes between the GPU and CPU. So you take a shape and you want to slice it to like remove the batch dimension. We would copy it to the GPU, remove the back dimension, then copy it back to the CPU and use it to fill a random normal. And that's just sad. So what we did instead in TensorFlow to kind of paper over this, and this is really sad because this would create a lot of like host device transfers. And every time you have one, you have to sync the GPU stream and you slow everything down. So to avoid this, we say that for almost every op that has a kernel registered on the GPU, that has int32 inputs or outputs, those are force placed in host memory. including things like plus, gather, reductions, and other things that you'd like to use as part of a model. Currently, the workaround is use int64 for types that you actually want to get executed on the GPU, and use int32 only for your shapes. We have a fix forthcoming. We have code already that exists in both Grappler for the graph mode and the eager placer for eager mode that uses some heuristics and estimates of the cost of transfer versus the cost of computation to try to keep small integer computations on the CPU where they belong instead of bouncing them back and forth to the GPU. But there's still some performance regressions that prevent these things from being turned on by default, but I expect it to happen very soon. So this is it. If you have any questions.
So could you maybe comment on the difference between the kernel cache and the caching that we do for functions and the Python layer?
So the Python layer does a caching for functions from the, like, here is a Python function, all these metadata that's completely invisible to the runtime, to a concrete function definition. When you go execute that concrete function definition, we emit a partition call-up or stateful partition call-up. That then hits the FE execute. And the first time the op has to execute, there's a lot of initialization that has to happen inside the runtime. That initialization is mostly covered by, a little bit of it's covered by the kernel cache that mostly tries to figure out what device that's going to be in and the dtypes of the attributes and things like that. And then the first time you actually execute it, we have the cache inside the functional library runtime, which is the thing that guards Grappler and all the other graph processing transformations we have to do. So it's a few layers of caches to make things fast. I don't really know how we could possibly merge these caches across these layers of the stack, but maybe if we unify more things, this is going to be possible.
And maybe it might be worth also talking, if you can comment a little bit about, so the kernel cache is something that is very unique to the eager execution versus something that we'd have in graph mode.
No, we already had the kernel cache in graph mode. I mean, we have a slightly different kernel cache in eager execution, but we already needed a kernel cache in graph mode too, because creating a kernel might require allocating memory, which might be expensive. It definitely requires allocating a vtable pointer, but in some kernels you have to allocate a lot more than that.
We just had some cases where there was memory bloat because of the kernel cache. Is there anything that users need to be aware of for that, or is that something that runtime needs to?
Hopefully, users should not be aware of it. There are some cases now where you have to be aware of it. Like if you're using the V1 random number generator ops, the only way to reset the random seed requires resetting the kernel cache because state's kept in the kernels. As we move to the V2 random number ops, we don't make this type of mistake. And so the space overall taken by the kernel cache should become much smaller. I also think for the particular case of functions, we should be able to garbage collect that cache a little better. Yeah. Okay. Oh, yeah.
So when XArray is enabled, we don't have this shape int32 problems anymore, right?
XLA has a different notion of kernel and computation. So by giving up the possibility of having any dynamic shapes at all, it can effectively, XLA only works when you can constant fold all the shape tensors away, and then it doesn't matter if you constant folded them on the GPU or constant folded them on the CPU, but they're not there. This is only a problem when you have runtime dynamic shapes.
Can you comment on the garbage collection in the runtime?
What
part in terms of what is garbage collected and what is the garbage?
Most of our runtime is ref counted, not garbage collected.
Oh, ref counted.
Yeah. There's a class in TensorFlow corelib core refcount.h. It's a base class for a ref counted pointer, and we use that instead of shared PTR because it's a smaller memory footprint and it has better cache locality behavior. So you should be able to just read that and find the places of the runtime that inherit from it, and you can see the things which are ref counted.
But we currently have no garbage collection for the kernel cache.
The kernel cache is not garbage collected, correct. But almost everything that can be ref counted already is ref counted. A few things, like the kernel cache, are not, because ref counting caches feels weird. But in some cases, like when you're caching the kernel for a function, it actually makes sense to ref count it.
Can we put a limit on the kernel cache?
In principle, we can do, yes. It's a memory versus performance trade-off. assuming we are not dealing with the V1 random number ops. Because those, if you are a victim from the cache, you now change the sequence of random numbers you would get, and that's pretty bad. Okay, thank you.